Okay, welcome everyone to the next installment of the RQC Quantum Seminar Series. It's my pleasure to introduce Dr. Ojas Parekh, who will speak to us today about algorithmic advances in quantum optimization and simulation. Ojas is a principal staff member at the Center for Computing Research at Sandia National Laboratories. He's a theoretical computer scientist who has worked in areas such as discrete optimization, quantum and neuromorphic computing, and graph algorithms. He's also currently the director of the FAR-QC effort, part of the RQC quantum computing effort funded by DOE. And he'll tell us about some of his research today. So Ojas, welcome. Please go ahead and share your slides. I will just quickly announce that our next speaker will be TBD at the moment, but will be on April 7th. This will get us back on our normal first Wednesday of the month time frame, and also give everyone, I think, time to prepare and get ready for March meeting. So I figured it would be good to skip through the normal busy month of March. So thank you and welcome, Ojas.
Thanks, Dave. Hello. All right. So I'm assuming these slides are visible. Thanks everyone for coming. So I want to tell you about some optimization work that's happened under the auspices of some DOE funded projects recently. As Dave just mentioned, I'd originally advertised some simulation work, and I realized that there was plenty of stuff to talk about with just optimization. So, not really trying to do a bait and switch here, but these things are interrelated, so we'll see what happens. So I want to first tell you about a project that recently ended, which is called Koalas, or was called Koalas. And this is quantum optimization in learning and simulation. And the idea here was really, we wanted to come up with new quantum algorithms from the interplay of optimization, simulation, and machine learning. So there are people who kind of work in each of these areas individually and, are making advances, but they're interrelated, and it helps to have people who kind of have all of these in mind, or some of these in mind, when they're designing algorithms to exploit connections. And so this was sort of our express purpose. And, we made some advances in all three of these areas. So today I'm pretty much going to be telling you about the optimization work in this project, and also in a related project called FAR-QC, which is, as Dave mentioned, it's an accelerated research for quantum computing project funded by DOE ASCR. And FAR-QC does basically look at kind of simulation, optimization, and machine learning algorithms, but there's sort of an additional kind of focus on a theory-practice interface. So, if we think about the spectrum of spectrum filling, kind of a physical quantum computer, all the way up to kind of ideal abstract quantum computers, where we design algorithms, there's quite a bit of a gap, right? And so if you're talking about ideal quantum algorithms, you're typically trying to prove asymptotic bounds on performance. And the hope is that what you'll do is you'll identify basic features of quantum resources that give you some kind of advantage. However, turning those kind of theoretical advantages into physical wins is challenging, challenging to impossible, depending on your perspective and experience. So, that's way up high in the sky, but kind of closer to Earth in a grassy layer, we could talk about, well, let me tell you about the ground first. So the ground are actual physical quantum computers, and here you have an instance of a machine, and you can code up some algorithm, and you can run various size instances, and you can see empirically what you get. But, it's really difficult or impossible to identify asymptotic advantages because you're only looking at kind of a finite size machine. And maybe these things grow over the years and you get some good kind of scaling that hints at what's going to happen, still you're ultimately looking at a finite size machine. And then of course, we all know that in addition to just being a quantum computer, there are all kinds of restrictions that are based on kind of resource constraints, idiosyncrasies of particular hardware or implementation methods, et cetera. So, then there's something somewhere in between, which kind of some people might call co-design, or kind of fits into that vein of research. But the idea is that you have physically inspired abstract quantum computing models. So you still have models, but maybe you've worked in some features or constraints that kind of reflect what's going on in reality. and these models are kind of enriched with those features. And so maybe what you want to do is still kind of try to do theory in these models, but you hope that you're closer to realizing practical wins if you're successful. And so FARQC lives somewhere between the grass and the sky. The idea is to bring kind of these, abstract algorithms closer to reality. So what we care about are things like resources, so if you have ancilla qubits, can we actually come up with kind of algorithms that have really good asymptotic performance, but, with a focus on reducing the number of resources required, like ancilla, et cetera. So this is something that we're engaged in, and is sort of an activity that's independent of kind of our other thrusts, but also kind of works within those. I'll also say, there's an idea here of, if we have good algorithms with asymptotic performance, that's great. Maybe we can turn those into practical algorithms. Maybe we can take the core ideas and kind of use those to inform practical algorithms. And vice versa, if we have methods that do really well in practice, can we put some rigor around them? So these are other things that we try and do in FARQC. We have a stellar team with participation from universities and the national labs. And then we have other organizations that are also affiliated with us. And as mentioned, our main research thrusts revolve around simulation, optimization, and machine learning, with also this eye towards theory and practice. And here are just a few of the topics that we think about, but we have kind of broad scope. So that's kind of telling you about the projects in which all of this work happened. But now I want to give you kind of a brief perspective on quantum optimization. So, what do we really mean by quantum optimization, and why is it a thing? So I as a computer scientist and outsider, I didn't really understand this until relatively recently. And this is really kind of what got me excited in exploring connections between optimization and quantum physics, or physics, more generally. But this idea that nature is constantly trying to optimize things, there's a fundamental connection between physics and optimization. So nature is trying to put physical systems into low energy states. Nature is great. We all love nature, but nature is not necessarily great at doing that. Nature gets stuck in local minima. And so it's a nice idea, but how well can you actually execute this? This becomes a challenge. And the other kind of interesting aspect here is, because we're talking about quantum physics, we sort of have a clear link to discrete optimization problems rather than continuous ones, because we have sort of a discrete number of quanta in whatever system we're talking about. So we could try this idea, right? We could sort of hack nature to solve our problems, and we could argue really that's what all of computation is just some kind of hack of nature to get something done. But in this case, what we try and do is we build a Hamiltonian where we have some classical problem in mind, and we map solution values to energy levels of a physical system. And we're not really trying to build a physical system out of scratch each time. Usually you have some physical system with knobs you can turn to kind of represent different problems. Then, once you've got this in hand, you let nature at it and see what happens. And, here I have an example where we're looking at the max cut problem, where you want to, I'll talk about max cut later, so I'll go ahead and define it now. But the idea is that you have a graph, and you want to sort of find a partition of the vertices where you want to maximize the number of edges crossing that partition. So it turns out that this graph here actually has a cut where you can include all the edges, where all the edges cross the cut. But it wasn't kind of obvious by looking at it. And, this not obvious by looking at it thing extends, and this is an NP-hard problem. It's also the basis of a lot of quantum optimization, because it's a well-studied problem classically, and it's an unconstrained optimization problem, which makes things a little easier to talk about. So if we're going to kind of represent this as a Hamiltonian, we could take a small graph, and we could talk about how different binary strings correspond to solutions. And then we can look at corresponding energy levels. And now you say, you want to find kind of a ground state of this Hamiltonian, and it corresponds to a maximum cut in your graph. And if your Hamiltonian ends up being diagonal in your preferred basis, then of course your eigenstates are just going to be basis states, classical strings. And so really, this is just kind of a classical problem, but you've kind of shoehorned it into this quantum setting. So it's a nice idea, but how well does it actually work? Well, heuristically we could try this, but we don't really expect quantum computers to solve NP-hard problems in polynomial time. On the other hand, as we know from quantum supremacy results, there are problems that quantum computers can solve efficiently that are very unlikely to be polynomial time solvable classically. These are like sampling problems or counting problems or things like that. They're not your typical decision or optimization problems. So one thing I'd like to mention here is that if we talk about the quantum approximate optimization algorithm, which I'll tell you about a little more in a few slides, there it's known this is one of the classes of quantum circuits where the sampling problem actually is likely hard classically. Like if you have even a low depth Quawa circuit, trying to classically sample from it or approximately sample from a state that such a circuit produces is likely classically hard. Bad things happen to complexity classes if you could do it. But on the other hand, that doesn't really tell us anything about kind of the efficacy of such circuits to actually solve optimization problems. So in some sense, all these supremacy results, they kind of sidestep optimization. And what the kind of prospect of speedups for optimization, exponential speedups or exponential resource advantages are wide open. We really don't have any examples in optimization where we have kind of exponential advantages. There's some you could call optimization. You could talk about query algorithms and that kind of thing. But for the most part, this is not something we really know how to do on a quantum computer. So using nature to solve optimization problems is a pretty old idea. You may have heard of this idea of using kind of soap film to solve Steiner tree problems, soap film computing, if you will. But as you could imagine, it doesn't scale very well. But in the quantum setting, it's actually kind of an idea that captures quantum computation. So the adiabatic quantum computation is a universal model of quantum computing, and it's very closely related to this idea of just letting nature kind of relax into a good state that represents the solution to a problem that we care about. Here with adiabatic computing, you have to give kind of a hint. You have to start with sort of a nice driver Hamiltonian and slowly work your way up to the hard one. But still, you could think of this as just some instantiation of an optimization problem, and it's really neat that optimization somehow fundamentally encodes what a universal quantum computer can do. And so if we take adiabatic and we discretize it, we end up with the quantum approximate optimization algorithm, which you can view as a trotterization of the adiabatic algorithm. And this is another kind of nice approach where it gives us a framework for representing discrete optimization problems and trying to solve them on a quantum computer. In terms of kind of rigorous results, there are very few known, and we don't have any where Quawa actually outperforms classical counterparts. There have been kind of these back and forth dueling banjo matches where we thought that Quawa was superior for a while, and then someone comes up with a better classical algorithm, and which is healthy, I guess, for both quantum and classical. But as of now, we don't know whether we can actually get sort of better approximation guarantees or better performance using this approach. But still, it's a very nice way of kind of talking about optimization through a quantum lens, and it's connected to variational algorithms and other things that people care about. So rightly so, it's been an object of study. So I've been talking a little bit about the tension between theory and practice, and here's kind of another instantiation of that. When I talk about Quawa or approximating a problem, there's this notion of an approximation algorithm that was kind of developed in the 60s and 70s. And the idea here is that you want to kind of bound the worst case performance of an algorithm with respect to an optimal solution. So, you basically look over all your instances and you look at sort of the optimal value for that instance, and then, some approximate value that a fixed algorithm is producing. And you look at kind of the worst case over all instances, and that's kind of your gap between your approximation and your optimal solution. And that's called your approximation ratio, of the algorithm. how well is it doing in the worst case? And so approximation algorithms are nice because they tell you, they give you kind of a hard guarantee on the performance of an algorithm, which sort of, seems too good to be true. And there are trade-offs because of this. But then on the other hand, approximation algorithms, I mean, on the surface, if you tell someone, hey, I have an optimization problem I want to solve, and I'm designing a way to approximate it, or if I tell someone I have a heuristic, I mean, it sounds like you'd be doing the same thing in all of these cases, but I just want to point out, sort of almost a perspective difference in kind of this sort of worst case approach, that's associated with kind of theory, and then kind of practical approaches that you would think of when you design a heuristic. So if you have a problem that you care about and you want to solve it, and someone's paying you for it or something depends on it, chances are you'll look at the instances you care about and you'll try to come up with some intuitive ideas to solve them. And then, your intuitive ideas will evolve and you'll do better. But somehow what you're doing is really guided by kind of these instances that you care about. And you don't really care about sort of contrived worst case instances. On the other hand, with approximation algorithms, you're really focusing on the worst case performance. So you have to kind of keep that in mind, either explicitly or implicitly, throughout the whole process. And these things are really designed with worst case performance in mind. And so mostly, in practice, they don't do so well as heuristics. But on the other hand, if you have applications where you really need hard guarantees, then you need something like this, and the idea is that can we really kind of marry the two? Can we use insights, mathematical insights that you get from approximation algorithms to come up with good heuristics, or can we try and bound the performance of heuristics that people are really using? And these are things that people try, but there are only limited cases where you meet with success. So this theory practice tension comes up all over the place, but this is something we're keenly aware of and we keep in kind of the forefront. So with all of that said, what really is quantum optimization? And there are kind of four natural candidates for, if you're talking about interfaces between quantum and classical, for what you might call an optimization problem. So you could talk about the algorithm that you have at your disposal, whether it's running on a quantum computer or a classical computer. And then you can talk about the problem that you have. Is it somehow a classical problem? Is there classical data that represents it, or is this what you would consider a quantum problem? And even that kind of boundary can be vague or kind of context specific. But just as some examples, if you have classical algorithms that you're using to try and solve quantum problems, well, one example of this are like classical approaches for quantum, for ground states or approximating ground states of quantum Hamiltonians. This is kind of like DMRG, density matrix renormalization group approaches, or mean field methods, more broadly fall into this class. Of course, you can also try quantum approaches for quantum Hamiltonians, and there's kind of less work in this area, but in principle, you can use adiabatic or you can use Quawa. You could to do this. You could use kind of quantum Hamiltonians and quantum drivers and see what happens. On the other side, if you have quantum algorithms on classical problems, that's sort of where most of what we call quantum optimization lives these days, where we're trying to see if quantum approaches can accelerate things we're already used to doing and things that already have applications that we understand. So this can take kind of a discrete form where we use adiabatic or Quawa, or you could look at quantum approaches for continuous optimization problems. And I'll talk about examples of all of these kinds of things throughout this talk. But one kind of challenge I want to leave with you all is that if we do talk about kind of quantum algorithms or even classical, I guess if we're just talking about quantum problems, there are many of these that come kind of naturally in physics, but at some broad level, we can just think of quantum problems as those where we want to produce some distribution with interesting properties and sample from it. And so the idea is, can we think of classical applications for such kind of sampling problems, that aren't necessarily motivated by physics? I mean, they may have connections to physical models, and that's great, but can we now start thinking about quantum problems, as having broader applications? So I think this is an area that makes a lot of sense these days, and I don't see too much work in. And by the way, please stop me if you have any questions or comments. I want to try and keep this talk informal to the extent that we can. Or you could send the questions in the chat, and maybe Dave will let me know. Okay, so now that I've told you a little bit about my perspective on quantum optimization, let me tell you some of the stuff that my group's been working on, and then I'm going to tell you, give you some highlights of broader work from these projects. So something I've become really interested in lately is quantum approximation algorithms. So approximation algorithms, like I mentioned, classically they've been studied for decades. On the quantum side, not so much. And here the idea is that we really want kind of rigorous guarantees. This is related to stuff that we think about in quantum physics, ground states of Hamiltonians or extreme energy states. But here the idea is, can we get rigorous guarantees on how close a solution is to the best possible? And with a lot of these problems, even identifying the best possible energy, just numerically what that value is hard. So typically you need some bounds on kind of the best energy, and then you have to work with those bounds. So, again, using max cut as a guiding example, we introduced a new variant of the Heisenberg model, which is really just a sign shift, but it has a closer connection to max cut, which these days we call quantum max cut. And, this is what I would call a syntactic generalization. So, I mean, what I mean by that is you look at the Hamiltonian for max cut in the Pauli basis, and it's I minus ZIZJ. And then you say, hey, to make it quantum, can I throw in some X's and Y's, And, it ends up that this ends up being an interesting problem, but, it's best seen as a generalization from the syntactic point of view when you're talking about polynomials and Pauli operators. So aside from motivation for solving these problems in physics, the real interest for us was seeing if we could take kind of discrete optimization techniques that have been developed classically, over the last few decades, and apply them to quantum Hamiltonian approximating extremal energy states. So one thing to mention here is that the Heisenberg problem is the one where you get rid of this I and you just have kind of pluses here. You can have weights and other things to kind of decorate the problem, but this is kind of the core version of it. So in looking at this maximization version, all that happens is kind of the max energy state of this Hamiltonian corresponds to the ground state of your typical Heisenberg model. But what changes is that from an approximation point of view, the complexity of approximating these changes. So this is also something that's observed kind of classically, but by making this a maximization problem and adding this identity term, by adding extra energy, it makes the problem easier to approximate. And what I mean by that is you can get kind of a constant factor approximation, whereas for the usual Heisenberg model, your approximations will depend on the number of qubits you have logarithmically. So the result here is that if you're just focused on product states, then there are examples where a product state can't get better than half the quantum energy. And we show using classical techniques that there's a classical randomized algorithm that's always guaranteed to get you within 0.498 of the best quantum state. So, as far as worst case approximations go, this is about as good as you're going to get. And chances are there's some hardness results that may actually point to why you can't get better than this 0.498. It's probably the case that a half isn't the right answer, that there should be some gap here, because otherwise you'd end up solving some hard problem. So this kind of work, just employs generalization of classical semi-definite programming rounding methods. And we basically wanted to see how far we could push these and try to understand connections between quantum and classical problems. So, if we're trying to do this as kind of an enterprise, then how do you take problems that people have studied classically and turn them into quantum versions? So, as I mentioned before, in this case, you could kind of just look at the Pauli operators and see how to do it. But, you could also kind of think of sort of your constraint matrix that you get on a pair of qubits. So this is just like the local Hamiltonian term, on each pair of qubits. And the classical max cut term just has 2 1s on the diagonal and 0s everywhere else. And, it really corresponds to putting some Boolean function on the diagonal, because really all you care about are basis states. So you just want to find a basis state, that kind of optimizes this, gives you the maximum energy on this. In the quantum version, of course, it's non-diagonal now. And so a basis state isn't going to cut it. You're going to have a kind of quantum state, a general eigenstate with max energy. And then you can ask, well, if I just restricted myself to product states, what's the best I could do? And here's an example where you get kind of a gap of a half. So we could do the same kind of thing. We could look at kind of problems that people have studied classically, think of them as local Hamiltonian problems or other kinds of quantum optimization problems, where the classical version is diagonal. And then we could say, what happens if you kind of make it non-diagonal, but still preserve structure? And so one example here is if you just think about classical constraint satisfaction problems, then the way you model those is that they're diagonal terms where you really just have a single one on the diagonal. So they're rank one projectors. So now you could say, well, what if I just looked at general rank one projectors, as terms in my Hamiltonian, which is kind of a natural generalization of this diagonal case. And this was studied by Bravi, and this is what's known as quantum sat. This is the quantum sat problem. So random assignment here, is kind of putting a maximally mixed state down. Will give you a quarter of the energy here. So just trivially, you can get kind of a factor 1/4 approximation. So there's been a body of recent work that we've been involved in that aims to understand how these quantum approximations for generalizations of classical problems, perform. And so there's several kinds of cases that have been studied. And, among the most general is just the traceless two local Hamiltonian problem, where each term is just traceless. And this naturally corresponds to kind of the classical Ising model. And, classically it was known that there was kind of a 1 over log n approximation. And then Bravi, Gossett, Koenig, and Temme, they produced a quantum approximation that matched that factor, which was really nice within constant factors. Some recent work of ours kind of, for a special case gets a constant factor. But other problems that have been considered are just local Hamiltonian where each term is positive, or, the SAT version where each term has a rank constraint. And then also this kind of max cut, this Max Heisenberg problem, which is a special case. It's actually, I'm sorry, above here means this. It's a special case of this problem. So these have natural classical counterparts that have been well studied, and you can see that the activity on the classical side kind of died out. I mean, we reached our limits. Either we got the right answer or we exhausted our techniques in the early 2000s, where we're just now catching up on the quantum side. This is all very recent work. And a lot of what happens is you can generalize classical techniques, but they become much harder to analyze because you have many more parameters. So for classical problems, you may just have 1 or 2 parameters, but in the quantum version, you would instead have 30 parameters. And then, you have to play tricks to reduce that down. And numerical methods aren't as reliable. You're trying to compute expectations of randomized algorithms. They don't converge numerically, et cetera. So it becomes more important to try and prove analytical results, which is what we've sort of been doing lately. Whereas on the classical side, because they could just do things numerically, they didn't really care so much about proving analytical results. So it's kind of the same game, but things become a little different. What I want to point out, though, here is that quantum max cut, seems to be a very nice problem that captures kind of the hardness. All of these are QMA hard, but quantum max cut in general captures kind of the main difficulties in designing these kinds of approximations, and it's been kind of a model problem in some sense. So this is the first one we studied, and then a half approximation, as mentioned before, is the best you can do with product states. And then recently, in some very nice work by Anshu, Gossett, and Morenz from about a year ago, they beat the best possible product state approximations by using a different ansatz. So it's still a classical algorithm, but now you're outputting kind of a description of a quantum state. And Kevin Thompson and I recently kind of generalized this, one thing I should mention is the game here isn't trying to get like incremental improvements in these factors. It's really trying to advance our knowledge and techniques, So in a table like this, you'll just see improvements in numbers, but really what's behind there are of course, new ideas. And so the new idea between these two is how, to think about kind of monogamy of entanglement constraints from like an optimization hierarchy point of view, how to relate things people have looked at on the classical side to kind of quantum entanglement. And so we've gotten started on that, and I think that's a fruitful direction, for these kinds of problems. So I'll close this part of the talk just by mentioning, saying more about that last bit, which is the Unshu et al. Algorithm, and then also the algorithm with Kevin Thompson. What we're doing there is, instead of producing a product state, we're producing a state where it's a product of kind of 1 and 2 qubit density matrices. So we have the 2 qubit density matrices are just going to be kind of maximally entangled states. They're just going to be singlets, and then everything else is kind of a product state. And it turns out, this ansatz is enough to get us, you might conjecture it's enough, but we can actually prove that it's enough to get beyond this factor 1/2 that kind of, where we were stuck with just product states. The other thing I want to say is that if we can produce kind of entangled solutions, which is the ultimate goal, then why are product states still interesting? Is it still interesting just to think about mean field approximations? And the answer is yes, because what ends up happening, through a really neat result of Brandau and Harrow, is that when you get to large graphs, when you have graphs with large degree, then kind of product state approximations are the best. Entangled things don't really help much. And so if you really want kind of a universal approximation, that's going to handle any kind of graph, then you have to understand what's going on with product states, because that's what's happening when these graphs get large and dense. And so somehow, the entangled stuff is only happening in kind of a small regime. For some of the cases we've looked at, where you're just looking at kind of a star, which is just a graph. It's a tree where everything kind of connects to a single vertex. There, the transition from entangled states to product states only starts happening very early, where the degree is only like 6 or 7. So in some sense, you've really got to understand both the product state and other approaches if you want to come up with good worst case approximations. So what we did in this work was we basically looked at an optimization hierarchy, which is called the Lasserre hierarchy. There's a quantum version of it that others have introduced that's about, maybe 10 or 12 years old now in the quantum community. And, we wanted to understand how this hierarchy relates to entanglement constraints. And previously, all known approximations used kind of the first level. So the idea here is that these hierarchies are hierarchies of semi-definite programs. And the higher up you go in the hierarchy, the larger the semi-definite programs get. And if k is the level that you're on, the size of the semi-definite program is order n to the k. So k is in the exponent, and when you get all the way up to level n, you're solving the problem exactly. You're solving the quantum problem exactly. So the hope really is that at some low level, you're able to, kind of take advantage of sort of key features of the problem to get good approximations. And so that's the hope, but kind of analyzing these things becomes challenging. And even the first few levels, understanding them is challenging. So all the previous works were focused on the first level, and we started understanding how the second level works. And, we related it to the approximation of Unshu et al. So, basically the message here is that we really want to understand how to approximate kind of quantum Hamiltonian, extremal eigenenergy problems from a kind of a discrete optimization or semi-definite programming point of view. In some sense, this is because of these quantum hierarchies. This is also kind of universal for quantum problems. But there are a lot of challenges, and there's a lot we still need to learn. We're maybe 20, 30 years behind the classical folks, what was done classically. And so it's going to take some interdisciplinary work to really be able to address this. And it's great that we've got the interest of the community, and we're trying to recruit more people into these kinds of efforts. So maybe this is a good place to field some questions, but now I want to kind of spend the last 15 minutes or so talking about some broader highlights from Koalas and FARQC.
Any questions from anyone at this point?
I have kind of a general question. Maybe it's a bit too general, but if we have a classical problem, let's say like a discretized form of the Navier-Stokes equations, and we want to solve it using a quantum method, do you have any insight as to like a quantum annealing approach versus some other sort of technique?
Yeah, I mean, that's a good question, right? So like a more general version of your question is like, if you know, if you have a problem that's kind of been studied well classically, and you want to come up with sort of quantum approaches for it, where should you look? I don't have any general insight into that, but you know, you could try kind of the natural thing is you could see what people have been doing classically for it, and you could see if you can generalize that, you know, turn the classical stuff into quantum counterparts. So that's kind of a safe approach in some sense. You know, I mean, it's not safe in the sense that it'll always work, but at least you're building on a foundation that exists. You know, a danger in that kind of approach is you might miss some really kind of disruptive techniques, you know, that are kind of quantum only. So, you know, it's actually a really good question that you ask, and I'm trying to think of if I know of any, you know, if I've seen any work recently where it's kind of like sort of a completely novel quantum approach, you know, versus sort of relying on kind of classical
It seems like you have a few folks who are trying like quantum annealing or adiabatic computing. Forgive me if I'm mixing the terms incorrectly, but and then you have another group that's sort of doing HHL and VQLS and those types of approaches. And I've been kind of looking more at the latter, but is it perhaps better to think of the former? I'm not sure.
Yeah, you know, I mean, I don't know, right? But all I could, I mean, it's kind of, we're sort of at a disadvantage because we can't just do, you know, like what you do classically, which is just sort of, you know, try them all and see what works best. I mean, we're really limited. But, you know, it'd be great to hear if others have insights into this, but I don't know of anything other than just kind of simulating or you know, using some knowledge that you might have to think what might be better, you know, short of just trying them all.
Thank you.
Yeah, thanks for the question. So, you know, here I've collected a few highlights that kind of speak to the breadth of the kind of optimization work that we've been doing. So this one is from Maryland, and the authors are listed below. And the idea here is that, you know, can we use quantum algorithms for convex optimization? So convex optimization is kind of one of the broadest classes of optimization problems that we know how to solve, you know, efficiently classically, right? So I mean, efficient may mean different things to different people, but in this case, you know, from a worst case point of view, at least, efficient means that you have kind of a polynomial time algorithm. And you know, to be fair, convex optimization is something that ends up working out well, kind of practically too. So it's a nice, you know, it's a nice kind of point of synergy between theory and practice. It's just a class of optimization problems that's very useful, that has ties to other things like machine learning, and then we can do well. So, you know, can we do it quantumly is a natural question. And so the Maryland group, you know, they show that, well, yeah, you can get kind of a polynomial speed up, you know, but this is kind of a different model than what you might be used to. So the idea here is that, and this is, I just like telling people about this idea because it's something that optimizers know about that may not be familiar to a broader audience, but you know, for optimization, you could think of like fundamental sort of yes, no questions about an optimization problem. Like, you know, usually an optimization problem, you have some feasible region and then you have an objective function. And, you know, one question might be, is this point feasible? So it's just a yes, no question. You know, I mean, you could also look at kind of questions that have numerical outputs, but, you know, you could just say, what is the objective value of a given point you know, with respect to your objective function. So like just, you know, evaluating your objective function is just another oracle or question that you could have access to. And sometimes objective functions are specified indirectly, so this isn't kind of obvious. You know, maybe there's an algorithm that's actually executing to do that. But what's been observed is that many of these oracles kind of reduce to one another. So for example, you know, if you could just tell me, if you have an oracle that can just tell me whether a point is in a convex body or not, you can actually use that oracle under some restrictions to solve a convex optimization problem. Or, you know, another interesting one is maybe your optimization problem has many constraints, you know, or maybe they're really complicated and maybe you don't want to like list them all down or just think about them all at the same time. And so if you can give me an oracle where if I give you a point like this one here, you tell me either, yeah, that point is in my feasible region, or no, it's not. You know, that's called a separation problem. And kind of a general version of that is you say, no, it's not. And then you give me a hyperplane that separates your point from your body. And, you know, if your body's convex, you can always do that. So it was observed kind of in the early 80s that, you know, you can use separation to solve optimization and vice versa, that one of these oracles lets you do the other thing. And this is by use of the ellipsoid method. So the work here is that, you know, the result here is that using membership oracles and function evaluation oracles, if you use Jordan's gradient estimation algorithm, quantum versions of these oracles, you can get by with much fewer calls, you know, only a constant number of calls, instead of like a linear number of calls that you need classically. And then you can apply the same kinds of techniques, this ellipsoid method, and you get sort of a better quantum algorithm. So you know, this again, this applies to broad optimization problems. You know, this has some of the caveats that we are aware of from quantum algorithms, but it still shows us that we can do this. And the group also proves some lower bounds, you know, on what the best possible is quantumly. So also from the Maryland group are high precision quantum algorithms for partial differential equations. So PDEs, you know, I mean, there have been quantum approaches for ODEs, but for PDEs, it's kind of been, you know, there have been sort of more limited approaches. The idea here is that, you know, or the main result here is kind of an exponential improvement in the error. So, you know, the complexity depends on log of 1 over epsilon, whereas it depended on 1 over epsilon with previous approaches. And, you know, they're kind of, depending on the problem, there are kind of two approaches here. One uses grid-based, finite differences, you know, grid-based methods. And the other is using spectral methods where you use basis functions. You know, in both of these cases, you're going to end up with a linear system. And then you use kind of quantum linear system algorithms to solve the linear system. So these algorithms maybe are a little different than previous ones where they're outputting some state that kind of represents a solution, you know, much like the algorithm HHL and others for linear systems do. But on the, you know, on the other hand, it is providing an exponential improvement, has this potential for exponential improvement, you know, over previous approaches. So in work from Argonne, they propose a method for kind of enhanced hybrid classical quantum simulation of circuits. You know, the idea basically is you take a quantum circuit and you cut it and you split it into small pieces, and you can run each of these pieces on a quantum computer. Because they're smaller, you're going to have sort of better noise performance. You know, you can kind of use overall, you know, your circuits are smaller, so you could take better advantage of your qubits and everything else that brings. So it's a natural idea, but then, you know, you have to run these small circuits, and then you kind of have to do some classical pre-processing to put them together to get the correct answer. And one of the innovations here is that they're using mixed integer linear programming, you know, which is kind of a really useful kind of problem that people solve classically all the time. You know, they use, there's some very well-known commercial codes like Gurobi that do this. And this drives a lot of industrial optimization. You know, this is kind of very practical. In worst case, these are NP-hard problems, but practically we can solve large instances. And so they're using mixed integer linear programs to figure out how to optimally cut quantum circuits. So it's kind of a novel marriage of discrete optimization, to enhance hybrid classical quantum simulation. And they get some very nice results when comparing with the classical method, like a state vector simulation or whatever. And one thing I want to highlight here is that it's nice that their work was accepted to a traditionally classical, conference. And so this is another thing that we've been trying to do in this project, is kind of, send quantum results to classical conferences, in order to get more exposure and kind of promote interdisciplinarity. So in work from the Whitfield group at Dartmouth, they look at kind of limitations of quantum approaches to HartreeFock. So HartreeFock is sort of a starting point, for many applications. But recently, the Google group proposed using kind of quantum approaches to HartreeFock instead of kind of self-consistent field methods that are the standard classical approach. And they were kind of proposing it as a benchmark problem. And so what the group does is, what the Whitfield group does is that they show that, although HartreeFock may be a good benchmark, it's, quantum approaches for it are unlikely to have practical impact when compared with self-consistent field methods. So they identify some simple, small, and well-motivated examples where where convergence issues are exhibited for black box approaches. So they show, for example, the emergence of multiple local minima, which creates problems. So this is kind of reinforcing another message, which is, HartreeFock is NP-hard in kind of the worst case. And so you can try to use quantum computers to solve NP-hard problems, and you can expect to succeed in much the same way that people kind of classically solve NP-hard instances, heuristically all the time, but don't expect kind of results that work broadly or categorically. You're going to hit some limitations, and so here they've identified specific limitations, which is kind of nice to know. And then finally, in two results from the Rolando Sama, Yugit Subasi, and Anirban Chaudhary, they look at computing partition functions with mixed state quantum computing. So the idea here is that there's this DQC1 model where you really only have kind of one clean qubit, and then you have a mixed state on everything else, a maximally mixed state. And the question is, can you do anything interesting in this setting? And what kind of was observed early on is that this is useful. One thing you can do is compute traces or partial traces of unitaries. This is sort of something that's associated with DQC1. What the Lanel group does is they show how you can actually compute partition functions which are traces of non-unitaries, exponentials without a complex part. So basically the idea is that they use kind of decompositions, linear combinations of unitaries to represent this operator as a bunch of unitaries, and then you can use kind of the DQC1 trace facility to compute what you want. And a nice feature here is that they actually show that computing partition functions in this way, a version of this problem is actually complete for the class DQC1. So in other words, computing these kinds of partition function actually like characterizes what you can do in DQC1, which is nice to know. It gives us another way of thinking about DQC1. And so in general, we're interested in kind of intermediate models of quantum computation, kind of as, in short of being able to construct fully general and fault tolerant systems. So we look at NISQ now, but there are kind of other models too, that one could consider and that have been considered. So it's always great to understand more about these sorts of models. And then finally, also from Rolando and Yihit, they've recently looked at verification in the quantum linear systems problem. So the motivation here is that, usually when we're solving quantum linear systems in the HHL style, we care about things like the condition number of the matrix, sort of the error, the dependence on the error, the dependence on the number of qubits or the size of the matrix, rank, et cetera. They're kind of properties of the instance that we care about, and usually the algorithms, are designed with respect to those. And in many cases, we know of optimal algorithms. If you care about a specific parameter like condition number, we know how to do it optimally, et cetera. But recently, people have proposed variational and other approaches for solving linear systems, where you try and come up with an objective function where you're trying to, you could also think of this as kind of least squares approaches. An example is kind of a least squares approach to solving linear systems where, you turn finding a solution of a linear system into an optimization problem and then you're trying to minimize error from, the variables you're looking for to some solution of the linear system. And, this is a nice approach, and there are many ways you could do this, but we really want to understand, if you're going to do this variationally, what kind of roadblocks will you run into? And, what are the limitations, and how do these approaches compare against more traditional approaches like HHL and quantum simulation style things? So what they do is that they show that, if you have any quantum algorithm for solving linear systems where you need to actually verify the solution. So these variational approaches have to do that. They produce a candidate solution and they stop when they think they've gotten close. So you need to be able to know when you found a solution. So if that's something you care about, then you're going to require, basically as many applications of a unitary to produce the right-hand side, a quantum state kind of proportional to the right-hand side, as the condition number. So you're going to need to kind of your algorithm's going to have complexity that depends on the condition number of this matrix, which can be pretty large, and it kind of puts a damper on some of these proposed variational approaches. So it's definitely good to know, what limitations are, and this kind of puts variational approaches, proposed ones, on par with other approaches in terms of complexity. So I want to go ahead and stop there and see if folks have more questions. Thanks.
Thanks, Ojas. Very nice talk. Any questions? I guess while people are thinking, I'll ask sort of my own, maybe high-level philosophical question for you, which is, you mentioned these limitations on variational style algorithms, and there's been a ton of research, obviously, into them now. I don't know, what is your thoughts and perspectives on achieving quantum advantage with them? And I know it's really hard to prove complexity bounds, as you said, on these variational algorithms. I think we're studying, but it's a question of whether we're going to see something really, truly interesting out of them. Can you comment?
Yeah, and I think this is also kind of related to Dan's question. It's sort of, when you have heuristic approaches, what's the best you can hope for? And in this case, you're asking specifically about variational approaches. I don't really have anything more insightful to say than I think what's already been said, but I think there are things you can do, like you definitely, like Rolando and Yehid's result, you can try to understand what limitations are. For example, a nice thrust there has been for Quawa. These days we understand that for low depth Quawa circuits, you're not going to beat classical algorithms. At least from this worst case performance point of view. So, you really need to look at kind of log depth Quawa or beyond if you want to do that. And so results like that are really useful. It doesn't necessarily put a damper on kind of practical applications, but it's still good to know what sort of broad limitations are on, whatever approach you care about, like variational methods. The other thing is that, like with any sort of empirical method or heuristic, sort of what you're hoping for is just to find a killer app, and so maybe what needs to be done, and I think this is already done to some extent, but maybe more so, is kind of a co-design where people are looking at, applications and methods, in sync, right? Like you're really trying to maybe reverse engineer variational methods to try and produce, applications where they'll do well or something like that. And it's certainly not a new idea. This is a lot of what the quantum supremacy stuff is all about, but specifically for variational algorithms, there might be some new kind of insights or things we could take advantage of there. But beyond that, I don't really have too much to add. Good question, though.
Thank you. Any other last questions?
So I just kind of a very general question again. Do you have any thoughts on proving whatever that means, success on real versus simulated qubits, and whether it's regardless of the approach you take?
So do you? I mean, let me let's get in like an interactive protocol here. So let me ask you a question. So do you mean, like, as an example of what you're talking about, maybe you have some algorithm where, like, on ideal qubits or something, and according to simulations, it does really well. It does what it's supposed to. But then how do you realize that kind of practically?
Well, just in like kind of where we're going with all this, if I have moderate success with, sort of a very constrained problem that I get to work well on simulated qubits, does that have any value if I can't run it on real hardware yet?
Oh, okay, I see. Yeah, so right. So the obvious reason you do simulation is to kind of understand more about the hardware. But are there other benefits of kind of like doing these things on via simulation or something like that?
Yeah.
Yeah, I mean, it's a good question. So I think maybe, I don't know. So when you're trying to design algorithms, often what you want to do is you want to understand how things work on small instances. And hardware won't really, I mean, at least if you're trying to design like ideal fault tolerant kind of ideal algorithms for fault tolerant quantum computers, your hardware, all the other factors are going to conflate the main message. And so maybe simulation could be like a tool for algorithm design. I mean, maybe again, like a kind of synergistic process where you're sort of doing simulations to kind of understand things, to give you ideas, or maybe rule out certain ideas for algorithms.
Because without getting like weirdly philosophical about this, because running simulated qubits on a classical computer, isn't that still a classical algorithm?
Yeah. So I mean, you're not gonna, right? It would be very weird if you actually got some kind of performance advantage, running a simulation. So I mean, that's really not what you're going for, unless for some really odd reason, you have a confluence of events where something like that's possible, which I don't know of anything like that. So yeah, I mean, it's a good question. I don't really know, aside from insight into designing algorithms or testing hardware, or proving concepts. I'm not sure what people really use simulations for, or how they've been useful.
Thanks, Ojas. I think with that, we are right about at time. Very, very nice talk. So thank you very much. And we'll
Thanks,
see
everyone.
everyone.
I appreciate it.
Oh, I think my internet is busting up here. Sorry. So thank you all very much. Thanks, Ojas.
See you, everyone.
Thank you.